Welcome back to Math 40. Today we're going to begin our lecture by picking up on Example 5 Part D of Lecture Notes Week 14. So I do encourage you to have this set open and ready to take down some notes. So we're going to begin by taking a look at the equation and seeing what we can replace tangent by to make it easier on ourselves and so we can just focus on the algebra aspect of it. So notice that if I let y represent tangent of x, the equation is going to become a y squared plus y minus 2 is equal to 0. Now this equation we've already solved before. We factored out into the product of y plus 2 times y minus 1 is equal to 0. And then if we let y plus 2 equal 0 and y minus 1 equals 0, we get final solutions of y equals -2 and y equals 1. Now, ultimately what we want to work for is x. So at this point, y is completely isolated, which means we can bring back in what it represents, which is the tangent of x. So one equation that we're going to be solving is tangent of x equals -2, and then the second would be tangent of x is equal to 1. Now this second equation is pretty simple. Tangent of x is equal to 1 is something we have on the unit circle. In fact, if we take a look at it, we're looking for points or angles at which both the y and x axes are the same. So if we take a look at 45, which is the equivalent of pi over 4, we have radical 2 over 2 for x and radical 2 over 2 for y. So if we take the ratio of y to x, we're going to get a tangent value of 1. So one possibility is that x is equal to pi over 4. Another possibility is that x is equal to a 5 pi over 4, because at that angle we also have y and x values that are the same. So we get x is equal to 5 pi over 4. Okay, now notice it chose the radians in this case because they do tell us that we need to find all of the angles in the interval 0 to 2 pi. So that's why we kept the pi over 4 and 5 pi over 4 versus the 45 and the 225. Now for tangent x equals -2, that is not a value that we have on the unit circle. So we're going to rely on our calculator to help us find that. Recall that if tangent of an angle equals a value, we're able to find the angle by taking tan inverse of the value. So we're going to get that x is equal to tan inverse of -2. Now in order to punch it into the calculator, however, we have to go through a few steps. We're first going to find the reference angle, which I'm going to call x prime, and that's going to be tan inverse of the positive value. So instead of a -2, we're going to take a +2. And again, I'll go ahead and write here that this is a reference angle. Now if we go ahead and punch that in, we first just want to make sure that we're working in radian mode. So I'm going to take a look at mode and change that to radian before continuing. And now we can take tan inverse of 2, which gives us a reference angle of approximately 1.1071. Okay, so I'm going to round to the nearest 4 decimal places. Okay, and what does that mean about the angle x? Well, now we have to use a reference angle to help us find what that angle will be. Since tangent of the angle x is a negative value, we have to focus on the quadrants in which we have tangent being negative. And so again, if you remember the all students take calculus memorization device, we see that tangent will be positive in the first and third quadrant. That means that we're looking at angles potentially being in quadrant number 2 and in quadrant number 4. So in quadrant number 2, the way that we obtain the angle from the reference angle would be to take 180, or in this case pi radians, subtract away the reference angle, and that would give us x. So that means that x is going to be pi minus the reference angle, and that'll be a pi minus a tan inverse of 2, which we approximate it to be 1.1071. But I'll write it this way, and I'll punch it into the calculator as a whole. That way we get an approximate answer that's closer to the true solution, rather than introducing the error from this approximation. In quadrant number 4, we would have an angle that opens and terminates something like this. And that means we have a reference angle between the positive x-axis and the terminal side. Now, in order to get the angle x from that, we could take 360 and subtract away the reference angle, and that would give us x. So that would be in radians at 2 pi minus x prime, which means we're looking at 2 pi minus tan inverse of 2. Okay, so now we're going to rely on the calculator for this next part. So pi minus, and let's go back. Pi minus tan inverse of 2 is going to give us approximately a 2.0344. For the next angle, we have a 2 pi, so I'm just going to copy the first expression and insert a 2 at the beginning. So 2 pi minus tan inverse of 2 will give us a 5.1760. Alright, and so those are the 4 possible solutions that we get. The first 2 that we found were x is equal to pi over 4, x is equal to 5 pi over 4. The other 2 solutions are 2.0344 and 5.1760. We're now going to take a look at part E of example number 5. And this is the first time that we're actually seeing an angle that is not solely x or maybe solely theta. We actually have x over 2, and that's going to make a little bit of a difference in how we approach the problem. So the equation is 2 times sine of x over 2 is equal to 1, and we want to find all solutions that satisfy the equation. So what I'm going to do is break it down into 2 parts. The first step is to find all of the angles in the range of 0 to 2 pi that satisfy the equation. Okay, so notice what that means. If x is going to be between 0 and 2 pi, that means that x over 2 will be slightly in a different range. So 0 to 2 pi, x being in 0 to 2 pi, we can write as x is greater than or equal to 0 and less than 2 pi. If we divide all 3 parts of the inequality by 2, that means that we're going to get 0 is less than or equal to x over 2 is less than pi. So that means that the angle x over 2 has to be between 0 and pi. Alright, so now that we've made that observation, I'm going to go ahead and replace x over 2 by a, because that'll help me focus just on the algebra aspect of the problem. And so we'll have a 2 times sine of a is equal to 1, which means that we divide both sides by 2, and we get sine of a is equal to 1/2. Where a, since it stands for x over 2, has to be between 0 and pi. So what we're looking for is what angle in the range 0 to pi has a sine of 1/2. And so if we take a look at the unit circle, the range 0 to pi is focusing on quadrant 1 and quadrant 2 because 0 to pi ends there. And we want to find all of the angles with a y coordinate that is 1/2. Okay, so here's one of them. It happens at pi over 6. And here is the second one. It happens at 5 pi over 6. Okay, so that means that a can be pi over 6, or a can be 5 pi over 6. Okay, now we've solved for the angle A. That's not ultimately the variable that we're interested in. The variable we want is x. So we're going to replace back x over 2 for A. So x over 2 needs to be a pi over 6, or x over 2 needs to be a 5 pi over 6. We can multiply both sides of the first equation by 2 to get x equals a pi over 3. And repeat that same process in the second equation, and we get x is equal to a 5 pi over 3. Okay? So those are the two angles in the range 0 to 2 pi that are going to satisfy the equation. Okay, now we can use that to help us find all the other solutions. Alright, so if we go back to the equation when we had only sine of a is equal to 1/2, we said that would be satisfied by a being pi over 6 or 5 pi over 6. This is only in the range 0 to pi, right? So in 0 to pi. Now if we want to find all solutions, any angle that is coterminal to pi over 6 or 5 pi over 6 would satisfy the equation. So all solutions means that I would take the pi over 6 and add to it any multiple of 2 pi, because one cycle is 2 pi. So that means 2 pi n, where n could be 0, plus or minus 1, plus or minus 2, so on and so forth. Okay, so these are coterminal angles. Now because A is not the angle that we're interested in, we bring back what A represents, which is the x over 2. So x over 2 needs to be pi over 6 plus 2 pi n. And then we multiply both sides of the equation by 2 again. So on the left-hand side, we'll have x is equal to, on the right-hand side, we have to distribute the 2. So a 2 times a pi over 6 will give us a pi over 3, just like what we had here. And then plus, take the 2, distribute to the second term. 2 times 2 will give us a 4 pi n. And that's one equation, or one solution for x that will solve the equation, rather. The other one will come from, and here I'm going to color code so we know what came from what. This answer is coming from a is equal to pi over 6, which turned into x is equal to pi over 3. Okay. The second part of the answer is going to come from a is equal to 5 pi over 6, or in other words, x is equal to 5 pi over 3. So if we go through exactly the same process of now saying, well, all the coterminal angles will be 5 pi over 6 plus 2 pi n, and then replacing the a with x over 2 and multiplying 2 to both sides, we're going to get x can be a 5 pi over 3 plus 4 pi n. Okay. Through the same process applied on this second equation. Alright, for this next part, we're going to use trigonometric identities to help us solve the equation. And the reason why we want to use trigonometric identities is because we're going to have equations that involve either more than one trig function or more than one argument, meaning more than one type of angle. So in an equation, you always want to have the same trig function and the same angle. unless you can completely factor out one of the trig functions, which in this case we can't, right? So I'll just write it here as a note. To solve an equation, you always want to have one, the same trig function, and two, the same angle. So in this case, we have a cosine 2x is equal to cosine x. The cosine 2x, we can take a look at maybe like a double angle formula to see how we can relate it to something that involves just cosine x. So cosine of 2 theta has three angles that are, three formulas that are possible for it. The second one would probably be the most appropriate because we have 2 times cosine of the angle squared minus 1. Okay, so I'll rewrite it down here. Cosine 2x is equal to cosine x becomes a 2 times cosine squared x minus 1 equals cosine x by double angle formula. Okay, so now that we have it in this form, notice this is a quadratic equation because we do have the square of a trig function. In fact, if it's easier to help you with the algebra to just see variables, we can let y be equal to cosine x. And in that case, we're going to get a 2y squared minus 1 is equal to y. Okay. That lets us see a little bit more clearly that this is a quadratic equation. Okay, so how do we solve this? Well, one way to do it is by factoring, similar to what we did with example D, or example 5, part D. So in this case, that means that we have to subtract the y from both sides. So we'll get a 2y squared minus y minus 1 is equal to 0. Now, everyone has learned this a little bit differently. I like to factor by grouping. So what that means is I first look for two numbers that multiply to the products of 2 and negative 1. So that's a negative 2. And that adds up to the coefficient of y. So it adds up to a negative 1. So we think about what two numbers multiply to negative 2 and add up to negative 1. That would be a negative 2 and a 1. So now that we've found those two numbers, and let me just write this here in case you're using it as reference later, we can write this middle term as the sum of these two terms. So we're going to get a 2y squared minus 2y plus y minus 1 equals 0. And then we group the first two terms and the last two terms and factor out the GCD of each group. So in the first group, I can factor out a 2y, which is going to give me a y minus 1. In the second group, I can really only factor out a 1, because that's the only thing that they share in common. So we'll end up a 1 times a y minus 1. Okay, and then we factor out one more time, but in this case, we're going to factor the common binomial, meaning in this case, we have a y minus 1 and a y minus 1 as a factor in both terms, so we're going to bring it out. We're going to have a y minus 1 times 2y plus 1 is equal to 0. Okay, and now that we've factored it in this way, we can solve y minus 1 is equal to 0, or 2y plus 1 is equal to 0, because if the product of two terms gives you 0, then at least one of them has to be 0. Right, so we're very close to an answer for y now. We can add a 1 to both sides, giving us y is equal to 1. And in this case, we would subtract a 1 from both sides and then divide by 2. So it's going to give us y equals negative 1/2. So we've solved the algebra aspect of the equation. We now need to bring back in what y is representing so we can incorporate the trigonometric part of the equation. And I've run out of space, so I'm going to continue this on a separate sheet of paper. Okay, so y was representing cosine of x. So that means that one equation is cosine of x is equal to 1. The other equation is cosine of x equals negative 1/2. Okay, and again, I'm going to color code this so we know that, so we know what came from what. From y equals 1, we got this equation, cosine x equals 1. From y equals negative 1/2, we got cosine x equals negative 1/2. And again, the reason why is because we originally had replaced cosine of x with y, so we could focus just on the algebra aspect of the problem. Now both of these values, 1 and negative 1, we have on the unit circle. So cosine x is equal to 1, for instance, we just need to find all of the angles that have an x coordinate of 1. And so that's going to happen just at 0 and at 2 pi. If we go back to the requirements of the problem, they tell us that our answers need to be between 0 and 2 pi, including the 0 but excluding the 2 pi. So x is equal to 1, cosine x is equal to 1 is satisfied by only x is equal to 0 radians. Now for 1/2, we want to go and look at all the angles that have a negative x value, not to be confused with this x, but an x coordinate that is negative and that it's 1/2. So that is going to happen here at 2 pi over 3. It's also going to happen here at 4 pi over 3. Right, so we get x is equal to 2 pi over 3, or x is equal to 4 pi over 3. And so we have 3 answers that satisfy the equation in the interval 0 to 2 pi. Alright, let's take a look at part B now. Part B has 4 sine theta times cosine theta equals square root of 3. And again, the problem here is the fact that we have the product of 2 trig functions rather than just one, and there really is no way to factor it out so that we have the product of 2 things equals 0. So in this case, what we're going to do is we're going to apply a trigonometric identity to help us simplify this into an equation that has only one trig function. And to do so, I'm actually going to factor out a 2 from the 4 so that we have 2 times sine theta times cosine theta, and I've accidentally written sine twice here instead of sine cosine, is equal to square root of 3. And the reason why I'm doing that is because this 2 sine theta cosine theta is actually sine of 2 theta by the double angle formula, right? We have this part, 2 sine theta cosine theta, that should be equal to sine of 2 theta. So this is 2 times sine of 2 theta is equal to square root of 3. Okay, I'll go ahead and write justification for this part. This is by double angle formula. Now notice, this is the second time that we have to solve an equation where the angle is has a coefficient that is other than 1. So we have a 2 theta. If we want to solve this for theta being in the interval 0 to 360, okay, so for theta in the interval 0 to 360, that means that for the angle 2 theta, we're looking at a different range, right? Because this means that theta is greater than or equal to 0 but less than 360. If we multiply all three parts of the inequality by 2, we're going to get that 0 is less than or equal to 2 theta is less than 720. Okay, so when we solve for the final angle, we want to make sure that we take a look at all of the angles between 0 and 720. Okay. All right, so similar to example E, example 5 part E, that's to say, I'm going to let A represent 2 theta. And then we're going to get an equation 2 times sine of A is equal to the square root of 3 over, just the square root of 3 actually. Where this angle A, which is 2 theta, has to be between 0 degrees and 720. Okay, so if we solve for sine of A, we're going to get sine of A is equal to square root of 3 over 2. And now we can take a look at the unit circle to find all the angles that have a positive sign and that have a square root of 3 over 2 as a y-coordinate. Okay, so if we take a look at pi over 3, that has a y-coordinate of radical 3 over 2, and same for a 2 pi over 3, we have radical 3 over 2. Okay, so those are two possibilities. A is equal to a pi over 3, or A is equal to a 2 pi over 3. Okay. What we want to be careful here is that we're not done. And these angles are in the range 0 to 360, but we actually want all the angles in the range 0 to 720. So that means that we can complete one full cycle, that's 2 pi radians, or 360, and then go beyond that to an angle that is coterminal with pi over 3. And I apologize, this should have been in degrees because we are working with degrees. So let's just change this to 60 degrees. And this to 120. Okay. So if we take a look at what angle is coterminal to 60 degrees that has already completed one cycle, that would be 360 plus 60. Right, so that is going to give us a 420. So, or A can be 420. Or we're now going to take a look at an angle that is coterminal to 120, but has already completed the 360 degrees. So that would mean that we're looking at 120 plus 360, which is going to give us a 480. Right, and then from there are no other angles because if we complete one more cycle, that's already 720 degrees, and that goes beyond the upper bound of the range. So 720. Okay, now we can bring back the original variable theta. So that means that I'm letting 2 theta be 60, so I'm replacing back. And if I solve for theta, that means divide both sides by 2, and we'll get theta equals 30. Or, if we now focus on the second equation, and we let 2 theta be A, that means 2 theta is 120. And if we divide both sides by a 2, we're going to get that theta is 60. Okay, we're going to repeat the process with the last two. 2 theta is 420, which means that theta can be 210. And finally, 2 theta is equal to 480, which means that theta can be 240. Okay. Now, just to convince you that, or to convince ourselves that we've done this correctly, let's go ahead and replace these answers back into the equation and verify that that they satisfy. So let's change to degree mode. and we're going to type 4 times sine of 30 degrees is the first angle that I'm going to be testing. So sine of 30 times cosine of 30. And that is going to give us a 1.73 with some other decimal numbers. Next, I'm going to check what is the square root of 3 to see if the two sides match up, or if the two answers match up. And we see exactly the same thing, so that's a good sign. And next, we're going to check angle 60 degrees. So we'll repeat the process, except that I'm going to replace this 30 with 60, and same for this one. Okay, again, we get that 1.73 with some other decimal numbers, and in comparison to square root of 3, it's the same number. We have 2 more to check. Let's go ahead and check those. We have 210 for the next one. So we'll replace this with 210, and this with 210, which gives us same number. And last one is 240. And there it is. I've got all correct answers. Okay, now for this one, I'm going to write the final answer as a solution set, which means I'm going to use the set symbol, curly brace, and then 30 degrees, 60 degrees, 210 degrees, and 240 degrees. And that's one nice way to write everything compactly. Okay, let's take a look at the next example. Tangent of x plus pi over 3 is equal to secant x over the range 0 to 2 pi. Now thankfully here we have the same angle, but we don't have the same trig function, right? One has tangent, the other one has secant. And so we're going to look at the trig functions, at the trig identities, to see if there's anything that can help us. Now everything that relates tangent to secant, well, one of them is here under Pythagorean identities. And that is pretty much it. That's the only formula that we have relating a tangent to a secant. But the kind of main difference between the identity and what we have is that they give us, they involve a tangent squared and a secant squared. And we only have tan and secant. So in an effort to make it to that point, we're going to square both sides of the equation. Okay, so square the left-hand side and square the right-hand side. On the left-hand side, we're going to have to distribute. Okay, so we're going to do that. So we're going to write this as tan x plus radical 3 times tan x plus radical 3 is equal to secant squared x. Multiply tangent times tangent, and we'll get a tangent squared x. Multiply tan x times radical 3, and we'll get a square root of 3 tan x. Square root of 3 times tan x will also be radical 3 tan x. And finally, square root of 3 times square root of 3 will give us just a positive 3. Alright, so combining the like terms, which are the middle two terms, we're going to get a 2 radical 3 tan x plus 3 is equal to secant squared x. So now we're ready to apply the Pythagorean identity. Pythagorean identity says that secant squared of an angle is equal to tangent squared plus 1. So we're going to replace the right-hand side with that expression. And so we'll get tan squared x plus 2 square root of 3 tan x plus 3 is equal to a tan squared x plus 1. Notice what's really nice about this is that now if we subtract tan squared x from the right-hand side, we have to do it from the left-hand side and these are going to completely subtract out to 0. So we're just going to be left with the equation 2 square root of 3 tan x plus 3 is equal to 1. Subtract the 3 from both sides, and we'll get a 2 square root of 3 tan x is equal to negative 2. Divide by a 2 square root of 3 both sides, and we'll get tan x is equal to a negative 2 over 2 radical 3. The 2's can cancel out, giving us a final expression. Tan x is equal to a negative 1 over radical 3. Now again, we want to rely on the unit circle to help us find all the angles x in the range 0 to 2 pi that have a tangent of negative 1 over radical 3. And so one thing to remember is that tangent is the y-coordinate over the x-coordinate of the point on the terminal side in the unit circle. So we're looking for an angle such that when we take the ratio of y-coordinate to x-coordinate, it's going to give us a negative 1 over radical 3. Okay, so there are two possibilities for it. Either the y-coordinate is negative and the x-coordinate is positive, or vice versa. The y-coordinate is positive and the x-coordinate is negative. Okay, let's look at the first possibility where the y-coordinate is negative and x-coordinate is positive. Okay, so positive x-coordinate means we're going to the right. Negative y-coordinate means we're going down. So we're looking at either a pi over 6 or 5 pi over 3 to see which one of these two will satisfy that the ratio of y to x will be negative 1 over radical 3. Okay, so let's work with this one first. If we take tangent of 11 pi over 6, we're going to get a negative 1/2 over a radical 3 over 2. And if we multiply top and bottom by 2 here to cancel out the complex fractions, we're going to end up with a negative 1 over radical 3 because these 2's are going to cancel. And that is precisely what we have. So that means that x could be an 11 pi over 6. The other one is not going to be a possibility, and we can double check. And y over x would be a negative radical 3 over 2 divided by a 1/2, multiplied by a 2 over 2 top and bottom. And we're going to cancel out the 2, so we're going to end up with a negative radical 3 over 1, which is not the same thing as what we have. Right? So this one's not a possibility. And the 5 pi over 3 is not a possibility. Right. Now that was the case when y was negative and x was positive. Let's switch the negative to the x-coordinate now. So now we're looking for negative x, which would mean to the left, and a positive y-coordinate, which would mean up. So now we're looking at quadrant number 2, and in quadrant number 2, we want to find an angle such that when you take y over x, it'll give you a negative 1 over radical 3. And that's going to happen at 2 pi over 3. If we take tan of 2 pi over 3, we'll have a square root of 3 over 2 divided by a negative 1/2. That means multiply top and bottom by 2, and we get a square root of 3 over negative 1. Oh, actually, I think this one wouldn't quite work, right? Because we'll get a negative 3 over a square root of 3 over negative 1, which is negative radical 3. So actually, this doesn't work. The one that's going to work is the 5 pi over 6. Okay. If we take tangent of 5 pi over 6, we're going to get a y over x, so that's a 1/2 over negative radical 3 over 2. And that'll give us a, again, multiply top and bottom by 2. That's going to give us a 1 over negative radical 3, which is precisely what we're looking for. So that means that the other possible angle is a 5 pi over 6. Right, so writing our, we're going to write our answers, but then we'll write them after we have checked them versus the original equation. And we want to be careful before we would check against the original just to make sure that our answers were correct. But in this case, because we squared both sides of the equation, there is a possibility that we introduce false solutions. So we have to kind of discard any false solutions, which means that it's mandatory that we go back and check. Okay, so I'm going to write this down here. Alright, and again, I'm going to do this on a separate sheet of paper because I don't have a space. But let's start by checking the first solution, 11 pi over 6. Okay, so the original equation is tangent of x. That means that we're going to replace tangent of 11 pi over 6 plus the square root of 3. Is it true that that'll equal to a secant of 11 pi over 6? And, well, let's take a look at 11 pi over 6 on the unit circle. 11 pi over 6 is here. Tangent, well, it's a negative 1 over radical 3. So is it true that a negative 1 over radical 3 plus square root of 3 is going to be equal to secant of 11 pi over 6? Remember, secant is the reciprocal of cosine. So we're going to take the cosine, which is the x-coordinate, and flip it. Is it true that that'll equal to a 2 over radical 3? Okay, well, let's see. I'm going to multiply top and bottom by square root of 3 here, so we have the same denominator. And that is going to give me a 3 over radical 3. Okay, and again, I'll show some side work for that. Okay, so square root of 3 times 1 over, times the radical 3 over radical 3. We're going to get a square root of 3 times square root of 3 is 3, and 1 times square root of 3 is just 3. Okay, so that's how we're getting this here. Is it true that that will be equal to a 2 over square root of 3? Well, let's see. 2 minus a 1 will give us a 2. 3 minus 1 will give us a 2. And then over the same denominator, radical 3. So then we get 2 radical 3 equals 2 radical 3. Okay, so that agrees. That means that 11 over 6 is a solution, is a true solution. Next, we need to check the 5 pi over 6. Okay, so tangent of 5 pi over 6 plus radical 3, is it true that that is going to equal to secant of 5 pi over 6? Okay, I'm replacing the angle into the original equation. Well, let's check. Tangent of 5 pi over 6, here's 5 pi over 6. Tangent of it gave us the negative 1 over radical 3. And then secant of 5 pi over 6, we're going to take a look at the cosine and flip it. The cosine is a negative radical 3 over 2. So that means that we're looking at a negative 2 over radical 3. Okay, Now this negative 1 over radical 3 plus square root of 3 we had before when we were checking x equals 11 pi over 6. And when we simplified it, we actually got a 2 over radical 3, a positive 2 over radical 3. And that is not the same thing as a negative 2 over radical 3. That means that this one here is a false solution. So for our final answer, we're only going to have one solution, the 11 pi over 6, which I'll write here on this page as a solution set. We're going to take a look at one last example, 6D. And this is tan of 3x plus secant 3x is equal to 2. And we want for x being in the interval 0 to 2 pi. So let's first try to get rid of the fact that we have two different trig functions, and then we'll worry about the fact that we also have a coefficient other than 1 for the argument, meaning for the angle. Okay, so similar to what we had last time, we want to use the Pythagorean identity. So I need to somehow end up with a secant squared and a tangent squared. What I'm going to do here is I'm going to subtract the secant squared, the secant 3x from both sides of the equation. That way I can isolate the tan. And if we square both sides, we're going to get tan squared of 3x is equal to a 2 minus secant 3x times a 2 minus secant 3x. Now, if the argument here becomes too much, because it is starting to get a little bit complex, we can always replace it by a different variable. Like for instance, we could have let theta be 3x right from the get-go, and that means that we would have had a theta here and a theta here. So if you'd like to do that to make things simpler, we can. Yeah. And that way we can focus on the bigger picture. Okay, so tan squared theta is equal to the product of those two binomials we're going to have to distribute. That means that this becomes a 2 times 2, which is 4. 2 times a negative secant theta, so that's minus 2 secant theta. Same thing here, minus secant theta times 2, so that's minus 2 secant theta. Then secant times secant, negative times negative becomes positive, and we'll have a secant squared theta is equal to a tangent squared theta. Okay, we're going to combine the like terms, and we're going to get tan squared theta is equal to 4 minus 4 secant theta plus secant squared theta. Alright, now if we go back to the Pythagorean identity to remind us exactly what it says tangent theta plus 1 is equal to secant theta. If we replace secant theta with the tangent squared, it would happen at this term, but it would still leave a secant theta left over for us to get rid of. So instead of doing that, I'm going to replace the tangent squared theta. And I'm going to do so by first solving for tangent squared here in the Pythagorean identity, which means I need to be subtracting of 1 from both sides. And we'll get that tangent squared theta is equal to secant squared theta minus 1. So I'll replace that into here. This is secant squared theta minus 1 is equal to 4 minus 4 secant theta plus secant squared theta. Okay, and I'll write justification here. sorry, this is not double angle formula, this is Pythagorean identity. Okay, now what we can try to do is subtract the secant squared theta from both sides of the equation, because in doing so we actually completely subtract away the quadratic term, leaving us -1 is equal to 4 minus 4 secant theta, and that means that we're solving now for the secant theta. So I'm going to subtract the 4 from both sides, giving me -4 secant theta is equal to a -5, which ultimately becomes secant theta is equal to a -5 divided by -4. That's going to give us a positive 5/4. Now, remember the range that we're working with. The original range was 0 to 2 pi for x, right? So x was between 0 and 2 pi. For theta, theta is representing 3x. So if we multiply all three parts of this by 3, we're going to get that 0 is less than or equal to 3x, which is less than 6 pi. Or in other words, that means that we're looking for theta in the range of 0 to 6 pi. Okay, so all angles in that range, that give us 5/4. Secant of theta is 5/4. Now we're going to use the calculator for this because we don't have a 5/4 on the unit circle or anything close to it. But since calculators can't handle secant, we're going to change it to cosine, which is its reciprocal. So we're going to find all angles that have a cosine of theta is equal to 4/5. Okay. Alright, so first we find the reference angle. The reference angle will be cosine inverse of 4/5. So make sure that we're working in radians again, because they do want the range to be 0 to 2 pi. Okay, so cosine inverse of 4/5 is going to be a 0.6435. And that's an approximation. I'm actually not going to be using the approximation, but I did want to show you what it is on the calculator, because since it's a reference angle, we're going to be using it to find the actual angle. And the actual angle has a cosine value that is positive, so that means that we could either be looking at quadrant number 1 or quadrant number 4. So in quadrant number 1, the reference angle and the angle itself are the same. So this is for quadrant 1, which is approximately, we've already calculated here, 0.6435. In quadrant number 4, we calculate the true angle by taking 2 pi and subtracting away the reference angle. So it'll be a 2 pi minus cosine inverse of 4/5, and that is going to be approximately, let's go ahead and insert a 2 pi into here, so 2 pi and then minus cosine inverse of 4/5, and that'll be approximately 5.63968. Now remember, these angles are just between 0 and 2 pi. They're in the range of 0 to 2 pi. But we need all the angles that are in the range of 0 to 6 pi. So that means in the range of 3 full cycles. And we only have 1 cycle currently. So to get the other 2 cycles, what we're going to do is we're going to look for all the angles that are coterminal to the angle in quadrant 1, which is this cosine inverse of 4/5. And the second one being the 2 pi minus theta prime, the reference angle, which turned out to be this 2 pi minus cosine inverse of 4/5. And so in the range of 2 pi to 4 pi, okay, because these are from 0 to 2 pi, So we are going to get the first angle, and I'll start labeling these so that we can keep track of them. This was the first one, this is the second. The third is just going to be coterminal to the first. So it's going to be theta 1 plus 2 pi. And so that means that we're looking at theta 1 was simply the reference angle. So it'll be the reference angle theta prime plus 2 pi. And theta prime is this cosine inverse of 4 over 5. So we'll have cosine inverse of 4 over 5 plus 2 pi. And if we punch it into the calculator, let's see what we get. Cosine inverse of 4 over 5 plus 2 pi. That is going to give us approximately 6.9266, I'll say 9, to approximate it to 5 decimal places. Alright, now the fourth angle is going to be coterminal to the second, so it's going to be theta 2 plus 2 pi, which is a 2 pi minus theta prime. That's just for the theta 2 angle, and then we have to bring over the plus 2 pi. So that is in total a 4 pi minus theta prime. Which is going to be 4 pi minus cosine inverse of 4 over 5. And approximately, let's see what that gives us. So we've got 4 pi minus cosine inverse of 4 over 5. And that's 11.92286, 87 if we approximate to 5 decimal places. Alright, now in the range of 4 pi to 6 pi, that means that we're going to be adding 2 pi to theta 3 to get the fifth angle. And that is going to be a cosine inverse of 4 over 5 plus 2 pi, because that was the final outcome of theta 3. So I'm just taking this result and plugging it into theta 3, and then we have plus 2 pi for a final outcome of 4 pi plus cosine inverse of 4 over 5. And let's see what that gives us. Okay, so I'm just going to take the previous answer and change that minus to plus. We get approximately 13.20987. And one last one, theta 6. That is going to be our fourth answer, theta 4 plus 2 pi. Okay, so for that one we had a 4 pi minus cosine inverse of 4 over 5. Which means that we are now adding 2 pi to that result for a 6 pi minus cosine inverse of 4 over 5. And if we punch it into the calculator, let's see what that gives us. I'm going to use this result replacing the 4 for 6. We get approximately 18.20605. Okay, so we're getting 6 possible answers for theta. Okay, so those possible answers, I'm just going to list them all together here. Theta 1 was approximately, let's see, approximately 0.6435. Okay. Now if you recall, theta is not the angle that we're looking for. We're actually looking for the angle x. So we need to replace back what theta was representing. And for that we're going to use theta equals 3x. So here we have then that 3 times x, and I'm going to label it x1 because it corresponds with theta 1, has to be approximately 0.6435. And if we divide by 3 both sides of the equation, we're going to get approximately 0.2145. The next one, theta 2, was approximately 5.63968, which means that 3 times x, which I'll label x2, has to be approximately 5.63968. And if we divide that quantity by 3, let's see what we get. 5.63968 divided by 3, we're going to get 1.87989. Okay. Theta 3 was approximately 6.92669. That means that 3 times x, and I'll call that x3, has to be approximately that quantity. And if we divide that by 6, we're going to get that x3 is going to be approximately, let's see, 6.92669 divided by 3, 2.3088. Well, this actually is about 90. Now I'm trying to round to the nearest 5 decimal places, but that's going to be, turn this into a 0 and this into a 9. Alright, now we're just going to repeat the process for theta 4 and theta 5. I'll try to fix the glare here. Okay, so for theta 4 we had 11.92287. That means that 3 times x4 has to be that quantity. So x4 will be approximately 3.97429. Theta 5 will be approximately 13.20987. Okay, and that's going to mean that x5 will be approximately 13. Actually, so let me divide that by 3. So it's going to be approximately 4.40329. And last angle, theta 6. Okay, we divide that by 3. And we get approximately 6.06868. Okay, now here's, it's been quite a long problem, but we have unfortunately some more work to do. And that is because we squared both sides of the equation in the very beginning, there is a potential that we introduce some false solutions. So we're going to have to check all of these. We're going to have to check all 6 parts, and by plugging them back into the original equation. Okay, so check the answers. By plugging them back into the equation. So I won't go through that work. I'll let you guys do that on your own, but you are going to find 3 false solutions. The only ones that are true solutions are going to be the 0.2145, which is the x1. The other true solution is the 2.30890. Which is this one here. And the last true solution is x5, the 4.40329. So written as a solution set, this is what the final answer would look like. Okay. The rest of the answers, x2, x4, and x6, these are false solutions.